Good afternoon, everyone. I'm Jingtao Tang from East China Normal University. So our paper here is efficient hybrid projection for encoding 360 VR videos. So before we start, I'll make a brief introduction about how the 360 VR videos are presented. So first of all, we have a material ball, and then we wrap it with a spherical video material. And as a viewer within the ball, we can obtain 360 VR immersive experience by rotating our head to get the wanted field of view. So there arises the question of how to project the sphere surface into a 2D plane. So in this paper, we proposed a hybrid projection geometry for doing it. So talking about the projection geometry types, there are mainly two categories. The one is polyhedron family. You can see the cube-like and the octahedron-like and hexahedron-like geometries. And the other one is cylinder projection family. So according to the orientation of the cylinder, it can subdivide it into three different types. You can see how the geometries, how they look like, and when they expand it into a 2D plane. As we all know, the videos are often encoded, and we do processes on the 2D matrix. So nowadays, the ERP and the cube map are two most commonly used projection geometries for projecting the spheral surface into a 2D surface. So these two most commonly used projections representing these two families still have some many questions, many problems in them. So here, our paper focuses on the cylinder projection families and tries to solve the distortion existed in equirectangular as well as known as ERP. So it has a simple conversion formula, but had severe distortions on the polar area. As we can see from the right figure, the original red dots in the sphere surface are expanded into two lengthy bars, as you can see. So we came up with this idea by using a transverse and an equal area projection, which is TCP in the bottom, and to store the polar area of the sphere surface, and maybe we can solve this distortion problem. So in order to make a thorough analysis between these projection geometries, we used two terms to describe the distortions in the conversion process. The linear stretching ratio evaluates the one-dimensional distortions, and the area stretching ratio evaluates the two-dimensional distortions. So using the mathematical definitions of them, we calculated the corresponding terms of some projections as listed in the table. So in order to make the comparison more convenient, we scaled all the lower bounds of linear stretching ratio and the area stretching ratio into 1, and by comparing the upper bound of each term, the smaller it is, the lower distortion it has. Here we demonstrate our hybrid projection briefly. So firstly, we use a latitude threshold to divide the sphere surface into 3 segments. And then, using the conversion formulas mentioned in the last slide, we project the sphere surface into the corresponding 2D rectangle. After we get these 3 rectangles, we hybrid them into a compact one rectangle. So in order to determine the latitude threshold, we plotted the linear stretching ratio and area stretching ratio of ERP and transverse cylindrical equal area projection. First, we focus on the ERP. The linear stretching ratio is well controlled as long as the pixels stay away from the poles, while the area stretching ratio is well controlled as long as the pixels stay around the equator. Then we focus on the transverse cylindrical equal area projection. The linear stretching ratio is well controlled as long as the pixels stay away from the equator. And since it is an equal area projection, the area stretching ratio is always 1. So it has no distortions on the area distortion. So in considerations of taking most advantages from these two projections, as well as making our hybrid projection layout compact, we use 1/4 of pi and 1/6 of pi to divide the sphere. So after determining the latitude threshold, we designed 3 frame packing layouts for the hybrid projection. Here, we demonstrate them with an abstract scene. The first layout in the left are designed for 1/4 of pi, which consists of part 1 and part 2 from ERP on the right top figure, and part 3 and part 4 from the right bottom figure. The numbers alongside the geometry edge are the corresponding length, and the final width to height ratio is 1.71, which is quite close to 16 to 9, and it has 4 seams. Next, we see the another 2 hybrid projection layouts. The top one is hybrid projection layout B, are designed also for 1/4 of pi, which looks very lengthy and has a width to height ratio of 6.83, but it has just 2 seams. The bottom one is layout C. So this one is designed for 1/6 of pi. Compared to 1/4 of pi, it has more ERP parts, but less parts of cylindrical equal area projection. And the width to height ratio is 4.1, and it has 3 seams. So here we use a real scene video frame as the texture of the material ball, and as we can see, we can find out how it combines equator area from ERP and the polar area from the transverse cylindrical equal area projection. So by using a spherical color bar texture as the material, the discontinuity of geometries are presented clearly. And we can see the different seams existed on the hybrid projections. By using an evenly distributed red dots texture as the material, the distortions of geometries are presented clearly. And we can see the distortion of all the red dots on hybrid projection are being well controlled. And last, here we use area stretching ratio to encode a color saturation bar to better present the pixel density of the projection geometry. So we can see by storing the polar area of ERP with transverse cylindrical equal area, we can the pixel density of hybrid projection is keep balanced. So in our evaluation, we use the 360 library and PSNR-based BD rate to make quality comparisons between each projections versus the ERP. The vertical axis shows the BD rate reduction, and in this metric, more reduction yields better quality. So the horizontal axis shows 4 different PSNR types used in 360 library. Here we just use one test sequence as example to see the performance comparison, and more results can be found on our paper. First, we see the transverse cylindrical equal area projection. So since it is a equal area projection, we can see that it has some performance improvement. So next, we see the hybrid projection BD rate reduction. We can see that it has huge reductions. And now we see two state-of-the-art equiangular cube map and seamless uniform mapping projection. So in some scenarios, hybrid projections are better than them. In conclusion of our paper, we compared and analyzed the linear stretching ratio and area stretching ratio between different projections. And we proposed a hybrid projection based on the ERP and the transverse cylindrical equal area projection to solve the the distortions existed on ERP. But there are still some unsolved problems. Firstly, is there any optimal hybrid latitude threshold with a compact frame packing layout? That still remains a question. Secondly, potential adverse effects brought by the discontinuity existed on the hybrid projection may be reduced by padding techniques. Last but not least, we hope to add some more user studies to test how the hybrid projection really works on real things. So that's the end of my presentation. Thanks for your time and attention. I hope our work will provide some inspirations, and yes.
Any questions or comments? Okay, so go ahead.
Hi, I'm Ashutosh. I'm wondering, did you compare your hybrid projection with the segmented sphere projection? Because they also adopt like hybrid projection.
Can you repeat that question?
So I'm wondering if you have compared your hybrid projection with the segmented sphere projection. This projection scheme was also adopted at
segmented
sphere projection.
Sphere projection, or the SSP, right?
Yeah.
We didn't compare these two projections, but we compared with the EAC and the cylindrical projections like ERP and EAP in our paper. But we'll try to we're going to make the comparisons. So in the later, okay.
I guess SSP and your projection almost have the same similarities in
yes,
terms
yes.
of the
I think
thresholding.
They also
and the areas.
They also the SSP also used the segmentation idea to store the yeah.
Okay, thanks.
Oh.
Any other questions? Okay, I have some small questions. If the camera movement, or if the omnidirectional camera movement is different from the situation that you tested in this experiment, what happens? So maybe, I guess there is some dependency to the movement of the omnidirectional camera in terms of the encoding efficiency.
You mean the movement of the
camera. So
cameras?
Yeah, you want to sort of propose a sort of method of encoding the omnidirectional video, but if the camera is a movement strangely or some weird motion of the camera is happen, so the result is a change or same or?
In our paper, we just we use normal videos to encode our encode our video frames. So I think that is a good question. So if we have a disoriented videos, like the moving cameras. So based on the motion of the camera, maybe we can change the orientation of the cylinder to fit on this kind of motion.
Okay, I see. So that's why I guess if you can estimate the camera motion, then you can switch the mode or way of the encoding. So depending on the motion, that is what I guess. Yeah, but it's an interesting research. Thank you.